Welcome and today's talk. I'm very happy to introduce Jens Hemelaer from University of Antwerp. And today's talk is about Toposes and arithmetic non-commutative geometry. Thank you.
Okay, thank you. And thank you very much for the organizers for inviting me. So I will talk about some toposes that appear in arithmetic non-commutative geometry. And this is joint work in progress with Morgan Rogers, and also based on joint work in progress with Aurélien Sagnier. So some background. So there was the arithmetic site, which was introduced in 2014 by Kohn and Gonzani in their approach to the Riemann hypothesis. And what is this arithmetic site? As an underlying topos, it is a category of pre-sheaves on a monoid, which is the non-zero natural numbers under multiplication. And this monoid is equipped with a sheaf of semi-rings. And then later an analog was constructed by Sagnier for imaginary quadratic fields with class number 1. With a nice kind of structure sheaf on it. And I did something similar with 2 times 2 integer matrices, but the latter one without notion of structure sheaf. And in all these cases that involve toposes are toposes of pre-sheaves on monoids. And my joint work with Morgan Rogers is what do these toposes look like of pre-sheaves on monoids. And the focus of this talk will be to look at the geometric understanding of these arithmetic sites over different base rings and the interaction between them. And there will be no structure sheaves yet, so that's something that we will have to do in the future. So I will start with a very, very short introduction to topos theory from a geometric point of view. So first, what are Grotenbic topologies? Well, if C is a category and U is an object of this category, then a sieve on U is a collection of morphisms with codomain U, such that if F is in the sieve, then F of the G is also in the sieve. So if something is small enough to go through the sieve, like a sieve in the kitchen, and you go even smaller, then they also go through the sieve. And what is now a Grotenbic topology? It's a collection of sieves called covering sieves, such that it has these 3 properties. Well, it has the property that the maximal sieve containing all morphisms is a covering sieve. This is the sieve generated by the identity morphism. Also, if S is a covering sieve, then it's also the restriction of S along a morphism is again a covering sieve. And the last one is if S is a covering sieve and R is an arbitrary sieve, then if R is locally a covering sieve with respect to S, then R is a covering sieve. So locally being a covering sieve, then it is globally also a covering sieve. And what is now a sheaf for a certain Grotenbic topology, J on a category C? For each object in a category, you get a set of sections for this sheaf over the object U. Then there are restriction functors, so a section over U gets restricted to a section over V if there's a map from V to U. And these restriction functions have the property that if you restrict twice, then it's the same as restricting along the composition. And if you restrict along the identity morphism, then it does nothing. And with these 2 properties, F is called a pre-sheaf, And now when is it called a sheaf? Well, if you have a covering sheaf and a family of sections for each or each object in the covering sheaf, and these sections are compatible with each other, which means that if you restrict to the same map in the covering sheaf, then they agree. If this is satisfied, then there exists a unique glued section S over U, over the object that is covered by the covering sheaf, such that if you restrict again, you get the original sections in the covering sheaf. And now we get to the definition of a Grotenbic topos. A morphism of sheaves is a function for each over each object that is compatible with the restriction functions. And then we write sheaves over Cj for the category of J sheaves over C. And a Grotenbic topos is a category of this form. And also if two of these Grotenbic toposes are equivalent over Cj and Dk, then we say that C with the topology J and D with the topology K are Morita equivalent. So in some sense, study of Grotenbic toposes is the study of categories with Grotenbic topologies on them. But of course, if the toposes are the same, so if the two categories with Grotenbic topologies are Morita equivalent, then they are identified. Now we are going to look at different families of toposes to give some examples of toposes that you can work with. So the first one is topological spaces. If X is a topological space, then we can look at the pose set or the frame of open subsets. So you look at open subsets and the inclusion maps between the open subsets. And the canonical Grotenbic topology in this case, there's a Grotenbic topology such that a covering of U by smaller open subsets is a covering sheaf if and only if the union of all the UIs is again U. So this is the most obvious Grotenbic topology that you can think of. And then we use this notation for the category of sheaves on X. And here the topos has another description. The sheaves on X are the same thing as local homeomorphisms from Y to X. And that's an important thing to look at, because this essentially means that you can generalize the concept of local homeomorphisms to toposes by using this trick. And for a general topos, you can say that local homeomorphisms to these topos are the same things as objects of the topos. So we'll encounter this later. A more complicated example is this one, Equivariant Chiefs. If X is a topological space and G is a discrete group with a continuous left action on this space, then we define the category as follows. You take as objects, again, the open sets, but the morphisms are different. Instead of just inclusion maps, you're going to look at elements of the group that map the open set U in V. So basically, you not only take inclusion maps, but also translation maps by elements in the group. And the composition of two of these maps is given by multiplication in the group G. And this category has again a Grotenbic topology, and the covering sheaves are similar. These are the sheaves such that the union over all the images Gi over Ui is equal to the complete open set U. And this topos, we use this notation, and it's called the topos of G equivariant chiefs on X. So we're looking at the discrete group G here.
Is this name justified by some theorem that if you take a sheaf which is G equivariant, it will be an object of the topos, and conversely?
Yes, definitely.
Okay.
I'm not sure if I know a place where this proof is written out. I think Joshua Wrigley is now working with these things, and he is writing this out in detail, I think. So that would be good. Okay, pre-Shift toposes. So if C is a category, then there's also a topology such that only the maximal sieves are covering sieves. This is called the Pre-Shift topology or the chaotic topology. And this is good news because for this topology, the sheaves are exactly the pre-sheaves. So we don't need this third extra condition with gluings. And it follows that the category of pre-sheaves is also a Grotenbic topos because we have this category with the Grotenbic topology on it. Now, in a special case where C is a category with only one object, then we can identify this category with the monolith of endomorphisms of this object. So we, with some abuse of notation, we think of this category as a monolith. And we write that pre-sheaves on a monolith is the same thing as pre-sheaves on this category with one object. And as an example, the underlying topos for the arithmetic side by Kohn and Konzani is this topos of pre-sheaves, and you have a category with one object, and the monolith of endomorphisms are these natural numbers, non-zero, under multiplication. So this is a special case of a pre-sheaf topos, and we will see later that this is also a special case of a topos of equivariant sheaves. One of the most important lemmas in topos theory is the comparison lemma. And this tells us how to change sites. So if C is a category with a Grotenbic topology J, and D is a full subcategory, we think of D as a kind of basis of C, in the sense that each object of C has a covering sieve on it, which is generated by objects in D. So informally, you could say that every object of C is covered by objects in D. And then you get an equivalence of categories between these two toposes. For example, yes, if you have a basis for a topology, then this basis is a subfamily of the family of all open sets. And then the comparison lemma shows that you can define sheaves on a basis. And you can do something similar for G equivariant sheaves. As an application, suppose that X is a topological space, again equipped with a left action of a discrete group G. And now assume that this G action is a covering action. This is a terminology of Hatcher. Sometimes it's also called a properly discontinuous action. And what does it mean? You have a basis of the topology such that if U and G of U have non-trivial intersection, then G is 1. So G is the identity element for all open sets in this basis. For example, you can take the real line and take very small open intervals as your basis. And then if you translate these open intervals, then they will not intersect with the original open interval. So if this G action is a covering action, then the sets in this category that we defined for G equivariant chiefs, there's only one map between them at most, for between each two open sets. And this leads to an equivalence between the category of G equivariant chiefs over X and chiefs over the quotient of X by G, where this X over G has the quotient topology. So this definitely does not hold in general. In general, the G equivariant chiefs are a bit like a formal quotient of X by G, and the quotient X over G in the category of topological spaces is a much more coarse quotient. And as an example, you can look at equivariant chiefs on the real numbers for the Z action by translation, and then you get the same thing as chiefs on the circle. So now we will look at some toposes that are associated to Dedekind domains. And this is joint work with Aurélien Sagny. Of course, he did already some cases even with structure sheaf before I even started working on it. And then I did my paper with the 2x2 matrices. But now we are trying to do it in general for Dedekind domains and matrix algebras over Dedekind domains. So suppose that R is a Dedekind domain with field of fractions K. As examples, you can take the ring of integers of a number field, the coordinate ring of a smooth irreducible affine curve over FQ, or discrete valuation rings like the p-adic numbers or the formal power series over a finite field. Now we are looking at R submodules M of the vector space K to the N. And we say that this is full if the M generates K to the N as a vector space. So it's of rank N. And because R is a Dedekind domain, we have that the R submodules of this vector space are divisorial, and which means that M can be seen as an intersection of modules at each prime ideal of H1. So we can look at the local situation, the modules at each prime of H1. And these together determine the global situation, because you can write the global thing as an intersection of all the local things. We will now look at yes, smooth curve over the complex numbers is also a good is also a Dedekind domain, but we will see that we get into trouble later if we use complex numbers, because complex numbers have a topology on them, and this topology will not be reflected in the topos that we construct, which is not a good thing, I think. I think the topos should take this topology into account, but that's not the case yet. So we look at submodules, and we say in particular that this submodule is a lattice if it's full and also finitely generated. In general, we are not looking at only finitely generated modules. We are looking at all modules, and the lattices are the ones that are finitely generated. They are all lattices are projective because we're in projective modules because we're in a Dedekind domain. And now we consider the space X of R, and the points of the space are the full R submodules of this vector space K to the N. And the basis of the topology as a basis of open sets are these subsets for lambda and lattice. So a neighborhood is given by all the modules that contain a given lattice. These are in the same open neighborhood. And you can take the lattice always larger, and then the open neighborhoods become smaller. So this space XR that we defined is a sober topological space, which means that we can recover XR from the topos of sheaves on it. Or even more, we can recover the topological space by just looking at the lattice of open subsets. Because the points are just kind of intersections of the open subsets. Okay, what do we want to do now? We want to give a more explicit description of these full R submodules. And we first look at the submodules that contain a module of the form R to the n. And we are now going to look locally at the 8-1 prime ideals. So a module is given equivalently by a collection of modules over Rp, for P the prime ideal. Like this. And P ranges over the 8-1 primes. So it's an intersection of modules like this. So this is a result of Ortzel. And now this means that it is enough to look at each 8-1 prime separately. Also, by Morita equivalence, these RP submodules are correspond in bijective correspondence with the left submodules of the matrix algebra over RP that contain this matrix algebra and lie in the matrices over K. And in turn, these correspond to the left submodules of this quotient, because the submodules of the quotients are the modules that contain this MNRP. And from now on, we assume that the quotient of Rp by P is finite. So it has finite residue field for each 8-1 prime. And now we see that taking the curve over the complex numbers does not satisfy this criterion. But the other examples that I gave earlier, they do still qualify. So why do we do this? Because here, okay, we will see this later. The reason that we do this, that we ask that the residue fields are finite, is because then we can do Pontryagin duality. So for a uniformizer of this local ring, which is a discrete valuation ring, we call this uniformizer P, pi. And we can then write this quotient that we were looking at as a union of all these finite modules. So these are finite because exactly we asked that the residue fields are finite. And because we have this description of this quotient as a union, we can now apply duality. So Pontryagin duality is a duality between two categories. So the union becomes an inverse limit. And then you have also to take the Pontryagin dual of all these finite modules here. But Pontryagin dual of a finite module is again the same finite module. The duality is more explicit if you take if you put it in the denominator here, the pi to the k. So if you do this Pontryagin duality, what you get eventually is matrices over the completed discrete valuation ring RP. So this is the hat on RP is my notation for the completion of RP. And now it follows from Pontryagin duality for modules. So it was written out by Martin D. Leven, that the RP submodules of this quotient correspond to the closed right Mn RP submodules of this matrix ring over the completed discrete valuation ring. So this Pontryagin duality says that the subgroups of a group are the closed subgroups of a group are the same as the closed subgroups of the Pontryagin dual, and this says the same but with module actions on it. So if we look at these submodules, because the matrix ring over the DVR is dense in the matrix ring over the completed DVR, these are precisely the closed right ideals of MNRP completed. And what do these closed right ideals look like? Well, this matrix ring is a principal ideal ring. Every right ideal is principal. This was shown by Newman and Peirce. And further, if two elements of the matrix ring determine the same principal right ideal, then there is some unit such that AU is equal to B. So they are related by a unit on the right. And this is shown by Kaplonsky. So what does this mean? If you take everything together, that the R submodules of that contain R to the n are given by this quotient that we call U and R. And what do you have to do? You have to take for each H1 prime ideal an element of the matrix ring. This generates a principal ideal, and then you have to quotient by the equivalence relation multiplication by units on the right to get the set of principal ideals. And here is some shorthand notation where R with the hat on is the product over all completions at all H1 prime ideals. And now we want all full R submodules, so we have to allow some scaling by some element of the field. And this means that we get, for the space X and R that we defined earlier, that the elements are not just elements in R hat, but also they can have coefficients in R hat tensor K. And we use notation finite ideals over K. So here the words finite depends on R, so maybe it's not the best notation. For example, if you take R equal to Z, but with P inverted, then the prime ideal corresponding to P will not be finite. It will be a point at infinity. Now let's take a look at isomorphism classes. So there's a continuous left action of a GLNK on this quotient, These quotients are exactly the full submodules. And 2 points in this group action are in the same orbit if and only if the associated are submodules or isomorphic. So what's the topos describing the full R submodules up to isomorphism? That's exactly this topos of equivariant chiefs of GL and K acting on this space here. And now the question is, do we have an alternative description of this topos? Maybe I should say at this point that we define the topology on this space. But this topology is different from the usual topology. If you check it, it's even a non-Hausdorff topology. But if you look at the Borel sigma algebra generated by the two topological spaces, then that will be the same. So you could say that maybe measure theoretically they are the same space, but the space that we're looking at is a non-Hausdorff, while the space that the usual topology on this quotient is a Hausdorff topology. So do we have an alternative description of this topos of equivariant chiefs? So then we have to look at a basis for the topology and then use our description, our definition of the topos of equivariant chiefs together with the comparison lemma. So a basis of open sets was given by these, where for lattices lambda, and using this basis of open sets, we can describe this topos E as a topos of sheaves on this category. The objects are the lattices lambda. So these are correspond to the basic open sets. And the morphisms from lambda to lambda prime. These are elements of the group such that G inverse of lambda prime is contained in lambda. The reason why G inverse appears here is because we have to look at when this set here is contained in the corresponding set for lambda prime, which means that the arrows change direction. If you write it out, then you get this description. And these are precisely the injective morphisms of R modules going from lambda prime to lambda. All these injective morphisms are given by multiplication by an element of GL and K. And what is the Grotenbic topology? Well, if you have a sieve, it's a covering sieve if if all these open sets here associated to lambda I cover the open set given by lambda. So what does this mean? If lambda contains an M, then there is an element I of the index set such that Gi of lambda I contains M. And if you look at this, then you can apply this by taking M equal to lambda. And what happens if you take m equal to lambda is that there exists an I in the index set such that gi of lambda I is contained in lambda. And the result is that this topology that we just defined is exactly the pre-Shift topology. So if we now look at the category of rank and lattices, and as morphisms of the category, we take injective R-module morphisms. Then what we showed is that the topos of equivariant chiefs on this topological space is the same thing as pre-sheaves on this category, which category of lattices. And in the special case that R is a PID, then the only rank n lattice up to isomorphism is R to the n. And in this case, the category on which we take the pre-sheaves
PID is principal ideal domain, I presume.
Yes, if R is a principal ideal domain, then this category will be up to equivalence given by a monoid, and it's exactly this monoid. So every endomorphism of Rn is given by a matrix, an n times n matrix with coefficients in R. And because the R module morphism has to be injective, we need this extra condition that the determinant is non-zero. So here are some examples. First, if you take pre-sheaves on the non-zero integers, then you get this topos of equivariant chiefs, Q's, the units of Q acting on the non-zero rational numbers acting on this space here. You can do the same thing with n times n matrices over the integers. Then you get an action of GLn over the rational numbers on another space. And this is the one that Aurélien looked at and constructed the structure sheaf on. This the non-zero Gaussian integers are the pre-sheaves on this are also a topos of equivariant sheaves of the non-zero Q elements of Qi acting on the same kind of topological space. So, and S always means non-singular, and if R is commutative, this is a commutative domain. This means just removing zero.
Very far from a group. This is a monoid, of course, it's very far from a group in general, yes, yeah.
Which one?
This MNS of Z and so on. I mean, it's because you say determinant non-zero, but of course, this doesn't imply that they are invertible.
Yes, yes, indeed. So it's the intersection of the So it makes sure that the monoid is cancellative, but it's still not a group.
Sure.
So if there are questions about this, otherwise we go to the case where we look at the change of rings. And I just
want to say one small word. So what is surprising, if I understand well, in what you have explained before, is that a topos that was defined a priori from a topological space, which is non-trivial and so on, turns out to be a pre-shift topos.
Mm-hmm.
Yeah.
Yes.
And it is a pre-shift topos of a very special kind because it comes from a monoid.
Mm-hmm.
Yeah. Okay, good.
So I have written out some conditions on the topos of equivariant chiefs about when it is of the form of pre-sheaves on a monoid. And well, it's maybe as you expect, if you have a basis of open sets on which the group acts transitively, then you only have one object in your Grotenbic site. And then you need some condition on the open sets to make sure that the Grotenbic topology is the Pre-Shift topology. And this amounts to saying that the underlying topological space is what is called a B space. So the basis has to be a minimal basis, meaning that an open set cannot be covered by open sets that are strictly smaller. Yes, so we will look at what happens if you change the base ring. And this is joint work with Morgan Rogers. So then we first have to introduce geometric morphisms. If there are toposes E and F, then a geometric morphism from E to F is given by a functor in the other direction. And this functor is called the inverse image functor, such that this functor preserves co-limits and finite limits. And this generalizes the notion of a continuous map, because if X and Y are sober topological spaces, for example, they are both Hausdorff, then the geometric morphisms between the toposes are the same thing as continuous maps from one topological space to another. So the notion of continuous map generalizes to topos, and similarly also the notion of local homeomorphism generalizes to toposes. I won't give the formal definition here of a local homeomorphism. There's a question here. Thank you. Yes, so these geometric morphisms have adjoints. That's a good comment. So this functor F upper star, the inverse image functor, because it preserves co-limits and it's a functor between toposes, we automatically get that it has a right adjoint. This right adjoint is a F lower star. It's called the direct image functor. Sometimes the functor F upper star will also have a left adjoint, F lower shriek. And this is the case, for example, if F is a local homeomorphism. Now we will look at the root topos. So this was something that was introduced by Konen Konzani in 2019. For M, a monoid, let's look at the category of elements of this monoid. And what is this category? The objects are the elements of the monoid, and the morphisms are given by, if a morphism from X to Y is given by the elements M of M, such that Y times M is X. It's a bit like a Cayley graph for groups. So a morphism is given by multiplication by an element of the monoid. And the root topos is then defined to be the category of pre-sheaves on this category that we just defined. And what Morgan and I did was we showed that the root topos only depends on the topos of pre-sheaves on M. So it does not depend on the monoid M itself. This is only surprising if M does not have, if M has non-trivial idempotence, because if M does not have non-trivial idempotents, then you can recover the monoid M from the topos. But it's still true if there are multiple monoids giving the same pre-shift topos. There's a local homeomorphism between these two topos, from the root topos to the pre-shift topos. And we can think of this as a kind of universal covering of the pre-shift topos. Why? I'll say that later, maybe. So for now, it's just intuition. This kind of map was already looked at in the case for the arithmetic side by my PhD advisor, Lieve Lebrun. And he looked at this as the Diaconescu cover of the arithmetic side given by the big cell. So this is this is also an instance of this local homeomorphism here. So what happens with this local homeomorphism if M is, for example, the n times n matrices over a principal ideal domain? Then the root topos will be sheaves on this topological space U and R. And then we can also see that this has some kind of behavior of a universal covering. For example, it's contractible. It's only a contractible topological space for maybe trivial reasons. That it's contractible because it has a dense point. And all topological spaces with a dense point are contractible. But still, it gives some motivation for why you can think of this root topos as a universal covering. Also, you can look at the fundamental group of topos. And if you look at the topos of pre-sheaves, if you look at the fundamental group of the pre-sheaves on M, and M is a submonoid of a group such that M generates G, then what happens is that the fundamental group of this topos is exactly G. And on the other hand, the fundamental group of the root topos, because this space is contractible, this will be trivial. So that's how the analogy works, more or less. What more can we say about local homeomorphisms? We can, for example, look at the local homeomorphisms from one pre-shift topos on M to the pre-shift topos of N. So, good question. What about the covering transformations? So what happens if you have these root topos? At least for each element M in M, you have a map going from here to here. I'm not sure if you can also do this for elements of the group G. So how do you do this? This is a more technical formulation. But if people know about slice toposes, then you can write the root topos as a slice topos over the object M, seen as a set with a M action. And then this deck transformation is given by the map of left M sets given by sending X to, it has to be a map of right M sets, so it's given by multiplication on the left. So it's induced by this morphism of M sets. So the idea is in topos on a of sheaves on a topological space, you have that the objects of the topos are the same as local homeomorphisms to the topos. And we can do the same here. We can think of an object of the pre-shift topos, which means set with the right M action. We can think of it as a local homeomorphism over this topos. And maps of right M sets are then maps between the local homeomorphisms. So if M and N are cancellative monoids, then we can look at when a morphism, a geometric morphism between them is a local homeomorphism. And these are necessarily induced by an injective monoid map phi from M to N. And for this injective map phi, this even induces a commutative square between the on the upper level between the root toposes, and on the lower level we have the pre-shift toposes. And then what Morgan and I showed is that the geometric morphism F is a local homeomorphism if and only if the root of F is an equivalence of categories. So this uses some factorization results for geometric morphisms, and these factorization results you can find, for example, in Sketches of an Elephant by Peter Johnstone. So this geometric morphism is a local homeomorphism if the induced map on roots is an equivalence. So some examples, if you look at the non-zero natural numbers and you include them in the non-zero integers, then if you look at the roots, then they will both give the principal ideals of the integers. So for each natural number, you will have a principal ideal. And you can see that then on the root level, it induces an equivalence. And the same for if you look at this DVR included in the completion of the DVR, discrete valuation ring, then this induces a local homeomorphism on the level of pre-shift toposes, because it induces an equivalence at the level of roots. And also any inclusion of groups also induces a local homeomorphism. And we have similar results for a larger family of geometric morphisms, the locally connected geometric morphisms. So if F is a map between pre-shift toposes induced by a monoid map, phi from M to N, then F is locally connected, even only if it is locally connected at the root level. So what we want to do is we take properties and we check them at the level of roots. And some examples here are localizations. So if you look at the ring R, the non-zero elements of the ring R, you include this in the same monoid, but for with F inverted, then this induces a locally connected morphism at the level of pre-Shift toposes. And same for if you localize at the prime ideal, or if you at an 8-1 prime ideal, or if you just go to the whole the group of all non-zero elements of K. So these are all locally connected. And in the other direction, you can do something similar, meaning you can write these toposes for the monoids on the right as subtoposes of this topos of pre-sheaves here. So these are some more geometric properties that you can look at when looking at these different toposes of pre-sheaves on a monoid. Some question, what happens if you pass from the integers in a number field to the integers in a finite extension of the number field? Yes, good question. That's something I wondered about as well. For example, if you take this extension, so what I want to do is find an étale extension of rings. And I hope this one works. This does not define a local homeomorphism between the corresponding monoids or the corresponding monoid toposes. So the reason is because you have principal ideals so this geometric morphism is not étale or not a local homeomorphism. And the reason is because this inclusion map does not induce a bijection between the principal ideals of these two rings, at least not as far as I can see. Okay, so thank you for your attention, and thanks again for inviting me. And if you have questions,
thanks for the talk, which I enjoyed very much. We received already a few interesting questions, but is there any other question you want to ask, Jens?
Yes, there is one question I want to ask you, which is not directly related to your talk, but which is, okay, for instance, if you take the arithmetic site or these various toposes, which are pre-Shift toposes, it would seem quite natural, for instance, in the case of the arithmetic site, to relate the notion of sieve, which is very familiar in analytic number theory, to the notion of sieve in the Grotenbic sense. So what I have in mind is that, you know, if we consider the monoid of integers, when you define what is Grotenbic topology and so on, you were looking, in fact, at right ideals, I mean, at ideals, because here everything is commutative. So somehow the small things were the things which are multiple of an integer. I mean, the smallness was coming from being a multiple of something. And of course, then this means that, you know, when you do the Eratosthenes sieve, what you do is you start with a number 2 and then you eliminate all the multiples of 2. So you eliminate all the numbers which are kind of smaller than 2, which pass through this. So, I mean, it would seem very natural to look, in the case of the arithmetic side, for a precise link. In fact, I always wondered whether Grotenbic invented the name from the number theory situation, because in French it's called crible. I suppose, well, in English there is a similar name. So it seems to be very tempting to go further and to find non-trivial topologies in these pre-shift toposes that would have really arithmetic significance with respect to people who are doing number theory in the how to say analytic sense. I mean, of using these sieves and so on. I mean, there are all kinds of very sophisticated sieves. But for instance, I find it extremely satisfying that if one understands the notion of sieve of Grotenbic as being small and passing through the holes, then the Eratosthenes sieve becomes very natural somehow. I mean, so this is more at the level of intuition than at the level of a precise question. But
yes, certainly possible that that it's not a coincidence that the name is the same.
Yes, I always dreamed that Grotenbic in fact knew what he was doing, and he called crible because he had an example like that in mind. I mean,
Any more questions? Comment? There is one from Masoud.
Can one express the Dedekind zeta function in terms of this topos? Yes, so what you can maybe do is if you have, for example, R or I'll say PID. And what we can ask is that the quotient of R by F is finite for all non-zero elements F of R. And this is exactly the same condition as before, I think, because you can use the Chinese remainder theorem to write this as a product of quotients of R over powers of prime ideals. And then if all the prime ideals are a finite residue field, then this will be finite as well. Now you can look at this map that sends an element F to maybe the number of elements of R. And this encodes Dedekind zeta function because you keep track of the number of points in each basically the size of each element F. And then I believe the Dedekind zeta function is like this. But you have to sum over elements not of R, but R modulo units. So these are kind of the finite points in this space U and R that we looked at. Yes, probably. Yes. Or maybe it's easier to, no. So maybe I did some miscalculation here, but I think this works for if R is a PID or if R is n times n matrices over a PID. So in this sense, you can get a zeta function from a kind of valuation map like this. And of course, a monoid map like this has an associated geometric morphism. So, which means this topos is kind of fibered over the underlying topos of the arithmetic side, geometrically speaking.
Yeah, but I think the question was whether you can get this last piece of information from the original topos. And I sort of doubt this.
Yes.
Yeah, of course, if you add this additional structure, it's very clear. But, you know, I mean, it's, yeah, that was, yeah. I think for that, you will need a structure shift because I don't think you can do that without. I mean, I doubt it very much.
Yes, at least in the case of the arithmetic side, it's not possible. Maybe for n times n matrices, I would be more hopeful to.
And for n matrices, there is much better chance that it would work. Yeah, exactly. Yes.
Thank you.
Any more comment? Then I leave to Zhang to conclude.
Okay. Thank you, everyone. So we will have a talk. Sorry?
The question.
Yeah, the geometric theory that is classified by the Pre-Shift Topos over a monolith M is the theory of flat left M sets. So sets equipped with the left M action of the monolith and that are flat for a certain definition of flatness. Okay.
Okay, thank you. Thank you.
Thank you.
Okay, thank you. So see you next week.